Today, we're going to dive into one of the simplest but most mind-bending thought experiments in all of physics, the particle in a box. It sounds almost childishly easy, right? But believe me, this little box holds a secret that completely rewrites the rules of the universe as we know it. The whole setup is incredibly simple. Just imagine we trap a single particle inside a box with walls it absolutely cannot get through. That's it. But by exploring this one simple idea, we're about to stumble upon one of the deepest truths of reality. So here's the puzzle we're trying to solve. In our everyday big box world, a particle is super predictable. But what happens when that box shrinks down to the size of an atom? Well, the rules get thrown out the window. Our job today is to figure out what exactly fills in those question marks. Okay, first things first, let's start on some familiar ground. We need to lay out the rules for the world we all see and understand, the classical world. So the setup is easy. You've got one particle, one box, it can't escape. Seriously, just picture a marble rolling around inside a sealed shoebox. It can't get out, but inside that box, it has complete and total freedom. And in this classical world, that freedom is absolute. You could find that marble at any possible position inside the box. It can have any speed you can think of, which means it can have any amount of energy. You want it to have exactly 1 joule of energy? No problem. How about 1.00001 joules? Also fine. It's all continuous, it's all predictable. All right, but now for the fun part. We're going to shrink that box, way, way down to the atomic scale. And this, right here, is where all those comfortable, predictable rules of our world just begin to fall apart. This is the big question, isn't it? When the boundaries of your box are as small as a single atom, do those same rules of freedom and anything goes energy still apply? Well, as you've probably guessed, the answer is a huge, resounding no. And the reason is that the particle itself is no longer just a particle. Down at this tiny scale, it stops acting like a little ball and starts behaving like a wave. This is that famous super weird idea of wave-particle duality. And this isn't a wave in water, it's a wave of probability. Wherever the wave is high, you're likely to find the particle. Wherever it's low, you're not. So now that our particle is a wave, it has to play by a whole new set of rules. And to really get a handle on this, we've got a perfect analogy, a simple guitar string. Think about it. When you pluck a guitar string, it's pinned down at both ends, right? It can't just flap around in any random shape it wants. It's constrained. Our little particle wave is in the exact same boat. Here's how it works. First, we know for a fact the particle can't be outside the box. That means the probability of finding it right at the walls or beyond them has to be 0. So this forces the particle's wave to be pinned down to 0 at both ends. Literally, just like a guitar string is pinned down at the nut and the bridge. And the result of being pinned down like that, it's huge. It means that only very specific, perfect wave shapes can actually fit inside the box. You can have a single, simple hump. You can have 2 humps. You can have 3. But you can't have, say, 1.5 humps, because that wouldn't end at 0. These special allowed patterns are called standing waves. Anything else is just forbidden. Now, this guitar string analogy is great. It gives us a really nice mental picture. But how do physicists make this stuff precise? Well, for that, they have to turn to the official rulebook of the quantum world. Yeah, this isn't just guesswork or a neat analogy. There's a master key, a single incredibly powerful equation that tells us exactly how these waves have to behave. And here it is, the famous Schrödinger equation. Now, don't get hung up on all the symbols. Just think of this equation as a command straight from the universe. It basically says, you tell me the size of the box, and I will tell you exactly which waves and which corresponding energies are allowed to exist inside it. We're not going to do the math here, don't worry. The really important part for us is the answer. What pops out when you actually apply this incredible rulebook to our tiny little box? And the solutions are just elegant. The equation totally confirms our guitar string idea. Only very specific waves are possible. And mathematically, these waves turn out to be the simple, beautiful shapes of sine and cosine functions. But here's the real punchline. Each one of those unique wave shapes corresponds to one single, specific, allowed level of energy. And this, right here, this is the first huge takeaway from our little box. It's not just that some waves are allowed and some aren't. It's that energy itself comes in distinct packages. The universe doesn't have a continuous energy buffet. It has a set menu, and you can only order what's on it. Okay. So a tiny particle in a tiny box has to follow some word rules. Big deal, right? So what? Well, it turns out this simple idea doesn't just stay in the box. It scales up to explain, well, everything. So now we can finally go back and fill in the blanks from our original puzzle. In the quantum world, a particle can't just be anywhere. It can only exist in these specific states that are defined by those standing waves. And it can't have just any energy. Only certain, discrete, specific energy levels are allowed. Period. So why does this matter so much? Because an electron orbiting an atom is, in a very real sense, a particle in a box. The box is just the electric pull from the nucleus. This principle, which we call quantization, is the reason electrons can only exist in stable, well-defined energy shells around an atom. This is the bedrock of all of chemistry, the reason the periodic table exists, and the reason matter itself is stable. Just let that sink in for a second. This simple act of confining a particle forces reality to become discrete, to create specific, stable states. This isn't just some mathematical party trick. It is the fundamental reason that the atoms that make up you, me, and everything we can see are able to exist at all. The universe isn't some chaotic, blurry smear. It's built on these incredible, specific rules that were first uncovered right inside this tiny, imaginary box.